Hello everyone, so my name is Thiago Alegre. I'm from the physics department at University of Campinas in Brazil. And I want to thank the organizers for the invitation and for all their effort for keeping the conference alive, especially in this situation. But this, however, gives me a unique opportunity to say good evening, good night, and good afternoon, or even good morning to all of you. So I will talk about how to enable strong light and sound interaction in brilliant optomechanics and nanophotonic structures. So I'll begin just to show by showing the Photonic Research Center at Unica, which our group's part of. So we moved to this building in the end of the 2018, and the Photonic Research Center counts with has four groups. Works in optical communication, applied photonics, ultrafast phenomena, and our group, which is a device research laboratory that has 5 professors and dozens of PhD and postdocs, and some of them are not the students in this picture, and we couldn't update it due to the pandemic. If you think about optics and photonics, you can relate them to the idea of electrical and electronic devices. So in an electrical device, you can simply make transformation on the electrical current to rotate a motor or actually to heat something. But when you control the package, when you control the information, you can actually store it and use it in more unique ways. The same thing happens to optics. You can use that in a regular glass or reflection and refraction. But when you control the flow of light, you can actually store and transfer information and actually have unique opportunities. And most of this, the photonic community relies on some building blocks that are made of modulators, routers, photodetectors. And they came in most very different aspect ratios and devices, platform, etc. But most of them are made of like optical cavities and waveguides. And the success of the silicon photonics, or the holy grail of our community, is actually to build photonics chip that could interface with standard CMOS platform. But this also brings us a problem, because it came with lots of undesirable properties of silicon. But also, on the other hand, our hope is that our scalability and reusing the existing foundry infrastructure driven the community and has driven the community to search for fundamental properties that could enable functionalities required in silicon platform. This actually has led to a very successful plethora of silicon nanophotonics spin-offs. So, for example, here we have like a huge array of phase arrays, optical phase arrays, like more than 4,000 phase arrays built on a chip. And you can go up to like the quantum nanophotonics, where you can have like hundreds of devices and up to like 16 single photon sources on a single chip, passing through like flat metal lens and topological nanophotonics. And on our group, we also use this infrastructure, and we are looking to the coupling between the optics and mechanical modes. So we are looking to what is the so-called optomechanical resonators. And what is the idea of these optomechanical resonators? If you have like a motion of an object nearby an optical cavity, and if this motion is at a frequency omega m, what happens is that this motion changes the optical path length, changes the optical frequency. So if you are driving the system on a given frequency, it changes back and forth the frequency. This modulates the field inside the cavity, and which creates side bands. This, in fact, this dispersive behavior is analogous to the scattering process in billion waveguides. And actually, in last year, like 3 reviews came out that explored this interchange and interconnection between the Brillouin and optomechanical communities. So just a little bit of the advertisement. Our review actually has some simulation files on Zenodo that you can actually download and reproduce all the simulations on the paper. And what is important here is that, as in the optical case, to increase the coupling between optics and mechanics, you have to engineer the mechanics. So you have to be able to confine better the mechanical modes into your system. And this is what we are doing here. So I'll show you how to confine backward Brillouin scattering, or actually mechanical modes that causes backward Brillouin scattering on a silicon platform. So the idea is quite simple, is that you have a silicon waveguide which is connected to the substrate, which creates mechanical losses by a mechanical grating. So we actually import this idea from our previous results on the so-called bullseye structure, where the mechanical modes are close to the edge and are away from the pedestal by this, and isolated from the pedestal by this mechanical grating. And we also have this needed waveguide core support, which will pose a little bit of a tricky in our design. But if you just look to a single waveguide, like a floating waveguide, you can actually look to the optical domain and to the mechanical domain and choose the correct sweet spot for the backward Brillouin scattering in terms of the coupling, changing the dimensions of this waveguide. So we are fixing the height of your device layer, so we are just changing the waveguide with it. And you end up having, in the C-band, the best mechanical modes are this Lamb wave mechanical modes. So what we do is actually, okay, so here's our Lamb wave frequency, and we are trying to find a sweet spot for this mechanical grating to isolate this mechanical motion from its surrounding. So we dig into that very hardly, and we actually you can actually do this very easily once you know what you are looking at, and you can put your mechanical mode within this band gap structure and isolate the mechanical motion from the sideways. So, however, there's a little bit tricky because this waveguide core support supports and also have like Y-polarized mechanical modes. And our modes, since there's our Lamb wave, they are actually ZY polarized. So this is this colorful chart here, where each color represents a polarization. So in the case of the mode that we are looking at, they are in between the X, the Y and Z direction, these colors here. So this creates an avoided crossing between this mechanical mode and this mechanical mode, which then decrease the gain. But once you know how to do it, you can avoid it and create a structure that looks like this. And if you compare it to a simple structure where there's no mechanical Bragg mirrors here, you see that there's a huge increase in the localization of the mechanical mode. Here's like a dB scale. Huh? So you end up with a gain that is about 4 times larger than a regular device. Okay, and there's also something very, very unique here, that by tuning your laser in the C-band frequency, you can actually tune your mechanical mode by almost like 1 gigahertz and still be in the region or within this white region here, which is the band gap for this mode here. So we got gain over Q close to what is reported in literature from von Laer's experiments. But what is important here is that you we expect that you can get a much larger gain due to the increase in the quality factor. And so we fabricate this device and we are waiting to go back to the lab to start testing them. We also use the same idea of the bullseye and also this waveguide, but in a unique platform made of gallium arsenide. So gallium arsenide has a very unique properties which does not have, which we do not have on silicon. So it has piezoelectric effects on it. It can also be an active material. So we are exploring how we can go to very high mechanical frequencies on these gallium arsenide optical resonators. And we did fabricate this device, and we could measure mechanical frequencies up to like 3.3 gigahertz, which is one of the highest mechanical frequencies. We also saw some unusual mechanical shift, which are explained by thermomechanics, not by optomechanics. And I will go into that a little bit later. But what is important here also is that we dig into this device and we went to very low temperature. And we noticed we could show that our devices are not limited by the design. So there are other losses for the mechanics, which are reported on the literature, which prevent this mechanical motion to have very high Q at room temperature. But at low temperature, we expect to have a very large mechanical quality factor. And we hope also to then explore a proposal from our group, which is to create self-sustainable lasers in these active materials. So as I told you, this thermal behavior on the gallium arsenide actually creates a thermal force, which is what we are calling the bolometric backaction force here. So very quickly here, so the mechanical motion on the optomechanical side change the number of photons inside the cavity. This can change back the position, or actually drive the mechanical mode through radiation pressure force. But also this changes the temperature of the cavity, because there's always an absorption of the cavity, which then drives these thermal modes, which can couple to the mechanical modes. Actually, you see here, like this is the thermomechanical motion, and this is only the only the mechanical motion, and they are very close to each other. So, which gives you a hint that they will couple very strongly. So, this is our proposal model for this photothermal force. It seems very complicated, but in fact, it only says to you that you have an energy here, and this is the gradient of this energy, and this energy is proportional to the strain created by the mechanical displacement, which is convolved, of course, with the properties of material, with the strain created by the gradient of or the temperature gradient in the sample. Okay, so if you just like expand the expression, you end up with a force over the surface and a force over the volume. This volume force has already been reported before, but not this surface force. Okay, and we did this calculation, so we were like, okay, so let's try to prove that this is the correct form for the photothermal force. So we dig into this into detail for gallium arsenide discs. So if you look to the absorption, to the typical absorption in gallium arsenide discs and a typical gallium arsenide radius and device, you end up having that this photothermal force can actually surpass the radiation pressure force. And it's even larger than what was proposed before, that only took into account the gradient temperature on the sample. And more importantly, this gradient or this volumetric photothermal force. It can have a different phase when compared to the total energetic approach that we are proposing here. So they can have very different behavior for the mechanical motion. In fact, if you run these calculations for with these parameters, you would expect that actually the change in the mechanical alignment for a simple Gynoscience disk is actually dominant by the photothermal force, not by the radiation pressure force, which is this green line here. So what we did is actually we went there, fabricated the device, and we need first of all to characterize the absorption coefficient of our device. So we end up using the nonlinearity of our device, which can shift the optical frequency when you put more power. So this is the cold cavity transmission, optical transmission. This is the hot cavity optical transmission. So you have a dispersion due to photon absorption and Fourier dispersion, but you have also a change in the coupling rate. And by carefully characterize both of them versus the internal energy or the input power, so to speak, we can actually calibrate what is the absorption coefficient of our disk and what are the non-absorption part on the alignment of our disk. So, and if you use these values and all the other information from the simulation only, you can predict what is the photothermal force and the radiation pressure force when you are looking to the laser position according to the cavity. So this is the tuning between the laser and the cavity. And this is only a prediction that takes into account our model plus the measured absorption coefficient for this disk. And we went there and measure. So this is a measurement of our device. The mechanical modes are around like 274 megahertz. And this is done as a function of the detuning to the laser to the cavity. And if we just plot one of them, you would see an RF spectra, which represents this mechanical motion. So we can directly measure the alignment of our mechanical motion or mechanical mode here. So, and that's what we did. So we measured this alignment as a function of the detuning, and you can see here that they really match well. Okay, they both really both our model and our measurement match very well. So what we did is actually to grab the largest mechanical mode modification, mechanical alignment modification, and plot that as a function of the input power. So we repeat this experiment a couple of times, and again this matched very well with our model for the photothermal force. And so this actually validates our energy approach and shows that you need to take into account the surface force, not only the volumetric force, when you are calculating the photothermal force. Okay. Okay. Last but not least, we also everything that I discussed up to now is related to the dispersive optical mechanics, which changes the optical frequency when you introduce a motion to one of the objects. But you can actually have dissipative coupling. Okay. And what is so, and you can have also dissipative coupling. So, but what is this dissipative coupling? Oh, okay, let me just go back here. Okay, so let's just go back to the dispersive coupling. So when you have this motion, you change the optical frequency of your optical mode, but also when you have this motion, you can actually introduce, for example, scattering or absorption due to this object that is being introduced in your optical cavity. And when you do that, you actually modulate the alignment of your optical cavity. And this also modulates the energy inside the cavity, which can then create a modification, a back action effect, only due to dissipative optomechanics. Okay. So now you actually have the two effects together in most of the cavities, and up to now, when you want to calculate the coupling between the motion and the optical mode, you use the perturbation theory, electromagnetic perturbation approach, to calculate this coupling here. But this has a problem when you have losses in your system, and the losses are not negligible. So first of all, when you have losses, you do not have orthogonality in this relation that you use on typical Hermitian systems. So you do need to change your orthogonality relation, and what we use is this what is called bioorthogonal product to describe this non-Hermitian approach of our system. So here it seems just very simple, just like take the dagger out of here, but that's something that's been reported before. So if you stick with me and believe that this is the correct answer, you see on our simulation that this matches very well with experiments. So doing this bioorthogonal product, you can actually calculate the perturbation for your optical frequency, and the real part of it will give you the dispersive coupling, and the imaginary part will give you the dissipative coupling. So what we did is actually we looked into the literature and saw the largest dissipative coupling integrated photonics device that is on literature, which is called this split beam nanocavity, which is from Paul Barkley's group. In this system here, you have two beams which are split to each other, and the motion one of the beams changes the coupling in between the two, and of course changes the loss of the system. And there's also an experimental detail here that the gaps, the two beams are not aligned perfectly. They have a little bit of misalignment in the z direction, which actually improve the dissipative coupling. So I go very quickly here because my time is ending. And what I'm showing here is that the points here are our calculation for the Q factor. And these horizontal lines here are always the experimental results from this paper. And this yellow parts here are actually the uncertainty they have in the experiment for the Z gap that I showed you before. Okay, so this is the region of the confidence of where the experiment report very good results. So you see that it's still very large optical quality factors in this region. So this shows that for the dispersive coupling, both the Hermitian and non-Hermitian approach, they match very well. This is because of the high quality factor, and this has been used for more than a decade on most of the optomechanical devices, which always have very large quality factors. So this is extremely correct. However, if you look at the results of the Hermitian approach for the dissipative coupling, it predicts a very little, basically zero dissipative coupling. And this is only because your eigenvalue is imaginary. However, if you apply the non-Hermitian approach and the bioorthogonal, you get a very different result for the dissipative coupling, which matches very well with the experiments. This actually has an impact on the other area, which is the so-called plasmonic optomechanics area, where a plasmonic resonance, which has a Q of about like 6, couples to the motion of a BPT molecule that has this thiol group here, and a very high frequency, about like 47 terahertz. But what was important here is that the cavity, you can model this as an optomechanical system, but you have the cavity, which is this plasmonic resonance, and your mechanical motion will create side bands away from the cavity. And this is in scale, just so you have an idea of the values here. So if you calculate the optomechanical coupling, and you can predict the instability regime, or where you see like the scattering of this the sidebands efficiently. But if you go there further and calculate the dissipative coupling, is actually larger than the dispersive coupling in bare numbers. And this predicts a very different result for the mechanical alignment of your system, of this motion here, and also a very different power for the instability regime, which is measured on the experiments. And actually, if you go to the literature, you can actually see that this difference in power or resonance on resonance plasma has been reported before, but was not explained. So we do think that this is really due to the dissipative coupling in the systems. Okay, so I think I'm ending now. So I hope that I convinced you that dissipative coupling is very important, and we now have a perturbative approach to calculate it. And I also show you very high frequency Gynoscience mechanical modes, up to 3.2 gigahertz, which has very good optical quality factor and mechanical quality factors. I also show you that photothermal forces are not negligible, especially on a very low Q device. And our proposal for brilliant waveguide scattering with very large gains. Okay, so I just show you some of the related results on our group that you can take into a look on that. And of course, I thank you everybody for your attention. And I stick with our founding agency just to acknowledge them. And that's it. Thank you. Bye-bye.